So we'll go ahead and get started. Quick recap. Last week we started on metric spaces. And this is kind of a little bit of a detour. So far we've been talking about topological spaces. We put that on hold for a second. We're talking now about metric spaces. Completely different. Using high-level language, what's a topological space?
It's the least amount of structure you can apply to a set that preserves proximity between points.
It's the structure you provide to a set to talk about proximity between points. Continuous functions goes from one topological space to another topological space, and a continuous function preserves proximity, but enables us to talk about proximity. And then what does a metric space enable us to do?
Talk about distance.
Talk about distances. It's a stronger notion than just talk about proximity. If you can talk about distances, you can for sure talk about proximity. The inverse is not the case. Okay, so stronger notion, talk about metric spaces. Now let's remind ourselves exactly what was a metric. Intuitively, it gives us distance, but strictly speaking, it had to have these three properties. So what were the three properties of a metric? First off, let's just make sense of the definition again. So a metric on X, X is a set that we're defining our metric on. We're taking 2 points out of X, and our metric gives us the distance between them. So a metric on X is a function. We usually use D for our metric function, D for distance. Its domain is X cross X. It takes 2 points out of X, and then it spits out a real number, being the distance between them. So a metric is a function that takes two things out of X and spits out a real number, such that these three properties are held. Property number one. The distance between 2 points always has to be greater than or equal to 0, and it can only be equal to 0 if the 2 points were the exact same point. If you have 2 points that aren't the same point, the distance always has to be greater than 2. Number two, the distance function is symmetric. The distance from X to Y has to equal the distance from Y to X. And then finally, it satisfies the triangle inequality. The distance from X straight to Z always has to be less than or equal to the distance from X to Y plus the distance from Y to Z. If you take a detour, it could have only made it longer. Could have made your path shorter. And then we call X together with D a metric space. Anytime we use the word space in mathematics, it typically means we have a set and we gave it some structure. So we take X as a set, we give it D a metric, together we have a metric space. Okay. Two theorems that we proved last time. One was just a lemma, one theorem. We're not going to reprove them, but we'll for sure be using this. This might come up today, so I want to refresh our mind on it and get used to what it says again. So something we proved last time. U is open in the metric topology. Maybe put a pin in that for a second. What was the metric topology now? So since a metric is a stronger notion than a topology, we can use a metric space to generate a topological space. And how did we do that? Do you remember how we did that? We start out by defining a basis. So our basis beta, and beta was equal to the set of all the open balls we could make, x epsilon, where x was any point in big X, and epsilon was any positive real number. These were our basis elements. So in R2, what does that look like? And that's what we meant by standard topology in R2 this whole time. We may take the standard metric, the Euclidean metric, create your basis elements this way, and whatever that generates is our standard topology. Make sense? Yeah. So that's what we were already doing on R1, R2, R3. We already had this notion for generating the topology. So if you have we remember what these open balls are?
Yeah.
So this open ball, tell me in words what this is.
It's a ball centered at X with a radius that's epsilon.
Right, so this is going to be a set of points. It's going to be all the points whose distance from X is less than epsilon. So pictorially, if we're in R2, that looks like this. And it's all the points in here. Right? So, it doesn't matter what our metric is. This is what they would look like in R2 if we were using the Euclidean metric. We also talked last time about the Taxicab metric. If we were using the Taxicab metric, our open balls would look something like this instead. These would be all the points within some distance epsilon of X. So it doesn't matter what metric you're using for your ball. You just have some metric. So then the metric topology is the topology you generate using that metric. So you have your metric. With your metric, you know how to create open balls. Put all those open balls together in a set, call it your basis elements. Use those to create your topology. So that's how you can always get a topology from a basis. Or sorry, how you can always get a topology from a metric space. If you have a metric space, you for sure have a topological space. Okay. So, back to this. So U is open in the metric topology on this metric space. If and only if. So first off, when is U open in a metric topology? It's open if it can be represented as a union of open balls. That's how it's open in general. So that's how we get them in general. This is going to be a special case of that now. So U is open in the metric topology on XD if and only if for any point Y we pick in U. So here's my U, here's some point Y. I already know if Y's in U, it must have been in an open ball that we used to union up to get U. This is going to say something a little bit stronger. This is going to say, if for any Y you choose, I can create an open ball centered at Y with radius delta, such that that open ball is a subset of U. So Y being in U without the theorem, all that would guarantee us is it must have been in some open ball. What we proved last time is not only is it in some open ball, it is in fact for sure in an open ball centered at it with some radius. There's always some small enough radius I can find such that Y is in the open ball centered at Y, and that open ball is going to be a subset of U. That's what we proved last time. And so that's what we're going to be using. And then finally, what does this last lemma say? Let XD be a metric space. If Y is in an open ball centered at X with radius epsilon, then there exists some delta, some small enough radius you can choose, such that Y is in that smaller ball centered at it, which is a subset of the bigger ball. So we use this lemma to prove this. So the lemma says if I've got some open ball centered at X and Y is in there, I can for sure create a smaller ball centered at Y that's inside the bigger ball. So almost says the same thing as this. So I guess we won't need this because this gives us this. We used this last time to prove this, so we'll just use this. No reason we'll need that lemma today. All right, so I think that's it for our recap. And so we'll move into this section's material. This section is called properties of metric spaces. So we're going to be going over some of their properties. First thing, every metric space is Hausdorff. Now, strictly speaking, that sentence is nonsense. What we mean is that the topology generated by every metric space is Hausdorff. That's what we mean. Now, let's remind ourselves, what did it mean for a topology to be Hausdorff?
For any point you find, for any 2 points you can find, you can create neighborhoods around each point that do not intersect.
Perfect. For any 2 points I have, I can give them their own neighborhoods so that the neighborhoods don't intersect. I can house them off from each other. So we're going to prove that that's always the case if your topology was generated from a metric space. Okay, so start out. Let XD be a metric space, and let X and Y be any 2 points of big X. So I grab 2 random points, X and Y. My job now is to prove that I can find the neighborhoods containing those points that have no intersection. That's what I'm trying to show. So let epsilon be the distance from X to Y. So this distance right here, we're calling epsilon. So let epsilon be the distance from X to Y. Let B sub X be the open ball centered at X with radius epsilon halves. So, where is that? So we've got B sub X is the open ball centered at X. Its radius is epsilon halves. And then B sub Y is the open ball centered at Y. And its radius is epsilon halves. Notice that those 2 balls are going to be disjoint. I'm going to prove that they're disjoint by assuming they're not and seeing that gets a contradiction. So assume by way of contradiction that Z is in the intersection of those 2 balls. So wherever Z is, somehow Z is a point that manages to be in that ball, manages to be in that ball. Obviously I can't draw that because we're setting up an impossible picture and explaining why it's impossible. So then epsilon is equal to the distance from X to Y. That's by definition. Epsilon is equal to the distance from X to Y. I know because D is a metric that the distance from X to Y has to be less than or equal to the distance from X to Z plus the distance from z to y. Okay? Now, since z is in y's open ball, the distance from x to z has to be less than epsilon halves. Because it's in its open ball. It's within epsilon halves of it. I know my picture's not showing it, but we're saying since z's in here, its distance from y has to be less than epsilon halves. And since z's also in here, its distance from x has to be less than epsilon halves. So this distance has to be less than epsilon halves, and this distance has to be less than epsilon halves. So this distance plus this distance has to be less than epsilon halves plus epsilon halves. Epsilon halves plus epsilon halves equals epsilon. So I get epsilon is less than epsilon. Contradiction, that's impossible. It's exactly equal to. Therefore, our metric space is Hausdorff. Okay, so there was a nice simple proof. Now this tells us something nice. It already tells us that, well, how's the best way to say this? A natural question you might have is, could I generate every topological space from some metric space? Is that going to be possible for every topological space? Or are there going to be some topological spaces that it's impossible to generate from a metric space? What do you think?
It feels like I don't know all of the topological spaces. I'm sure there's.
Yeah, there's infinite out there, but maybe if we were clever enough, for any topological space you gave me, if I was clever enough, I could come up with some metric so that with that metric space we could generate the topology you're talking about.
Well, what if you get a topology that's not Hausdorff?
Exactly. So this already tells us that nope, there's topologies out there that can't be generated from a metric. Because if it could be, it would be Hausdorff. But there's many topologies out there that aren't Hausdorff. And so the answer is no. And so this gives us another way. These topologies that can be generated from metric spaces are, well, how's the best way to say that? I don't want to say that way. It's useful to know if a topology could be generated from a metric and to get that metric. That's a useful metric to have. Oftentimes that's a useful thing to do. And so this gives us a way of basically knowing not to waste our time with some of them. So if a topology can be generated from a metric, we call it metrizable, which is what the next section is on. Unfortunately, we're skipping that section. It's not part of your basic topology course. But, so that's what the next section is on. And if you're more interested in that, read the next section, I guess. Anyways, let's continue. So our next theorem here. So our next theorem is, let X be a metric space. Its metric we're going to call d sub x. And Y be a metric space. Its metric we're going to call d sub y. So those are metric spaces. Then f from x to y is continuous, if and only if, for every x and for every epsilon, there exists some delta such that the open ball centered at x with radius delta, when I run it through my function, is entirely within the open ball centered at f of x with radius epsilon. This, you might remember all the way back, one of the hardest things we came across was the epsilon delta definition of continuity. And we showed that our notion of continuity is the same as the epsilon delta definition of continuity. The epsilon delta definition of continuity is this exact thing, except for it's only talking about the Euclidean metric on R. So now we're proving a similar version of that theorem, but this one's going to be true for any metric space. So we're not just talking about the Euclidean metric on R, we're talking about any possible metric space you can think of. Pick your metric, pick the set it goes to. This is how you can test for continuity. Now, I know that's a lot to swallow, so let me redraw out a picture here to help us understand it. First off, topologically speaking, what does it mean for a function to be continuous?
The pre-image of open sets are open.
The pre-image of open sets are open. That's all it means for it to be continuous. So the pre-image of our open sets are open if and only if this horrendous condition is satisfied. Let's make sense of that horrendous condition. So we're talking about two topological spaces here. So we've got x over here. X is over here. Y is over here. And f is a function from x to y. So what are we saying? We're saying that the function f is going to be continuous if and only if for any x and for any epsilon you choose. So we pick an x, here's some random x, look at its image, x when we run through the function it ends up somewhere over here, which we're calling f of x. Over here, pick any radius around it you want. That's epsilon. Pick any radius around it you want. If our function is going to be continuous, then that means that there must exist some radius around x I can choose. Some radius around x I can choose, such that when I run it through the function, it lands entirely within this ball around f of x. Now when I run that through the function, it's not necessarily an open ball again, it's just some set. But if that condition is satisfied, then f is going to be continuous. That's what the condition is saying. So it says for any x, now look over here, pick any epsilon. Epsilon is our radius here. This is our epsilon. For any x and for any epsilon, there better exists a delta, that's our radius over here, such that when we run the ball with radius delta using x's metric, when we run that ball through the function, it ends up a subset of our initial ball that we set up using epsilon. Remember over here we're using y's metric. So this could be two completely different metrics. And we can still talk about continuous function from one metric space using one metric to a completely different metric space using a different metric. So, pretty amazing that we can do that. So that's what we're proving. I feel like you got high level intuition for what we're trying to prove. All right, so let's dive into it. So, we're proving 5.13, just so I don't get lost. Okay, so notice that this is an if and only if proof. How do you prove an if and only if proof?
Both ways.
Yeah, you assume this is true and show that implies this is true. And then assume this horrendous condition is true and show that implies continuity. Got to go both ways. So first thing I'm going to do is say 1, assume f is continuous. Assume f is continuous. And what am I trying to show? I'm trying to show that for any x you choose and for any epsilon you choose, I can always find the delta that makes this true. So assume f is continuous, comma, and let x be any point in big X you choose, comma, and epsilon be any positive real number you choose. I have no clue what x is, and I have no clue what epsilon is. Just some point in some real number. Okay, there's my x, and now we can start talking about this open ball over here. Okay, 2. Observe that the open ball, using y's metric, centered at f of x, I'm going to have to probably talk about this ball a couple times, so I'm going to name it once, so I don't have to rewrite all this notation again. Observe that the ball, I'll call it b sub y, equal to the open ball, using y's metric, centered at f of x, with radius epsilon, is open in y. So this right here, this ball, I'm calling my b sub y. Okay. Now, since I know b sub y is open, what do I know?
Its preimage that'll be open.
Its preimage is open. So observe that is open. 3. Then v equal to its preimage, the preimage of b sub y, whatever that is. So when I run this back through the function, my v could be something like this. I don't know. So then v equal to the preimage of y is open in x, comma, and I also know that little x has to be inside of v. Because f of x was inside b sub y, then little x has to be over here in v. Okay. Now, what do I know from this theorem? a set is open in a metric topology if and only if, for any point in there, I can find some open ball centered at that point, where the open ball is a subset of my set. So, since I know X is in V, I'm guaranteed that there must be some open ball centered at X that's a subset of V. So 4. Then by, I didn't figure out the theorem number. So I'm just going to call it theorem. I know, I didn't label it. We'll just, for the purposes of this class, just call it theorem 1. So then by theorem 1, not sure what's named in the book. So then by theorem 1, comma, there must exist delta in the positive real numbers such that X is in the ball centered, or using X's metric, centered at X must exist delta such that a ball using X's metric centered at X with that radius is a subset of V. There must exist some radius I can put around X such that that ball is a subset of V, comma, call the ball V sub X. So I'll call the ball over there, V sub X, just in case I have to keep talking about the same. Okay, so let's see, what was I trying to show? I'm done. 5. Then we have this. Then f of v sub x is a subset of f of v, which is equal to v sub y, which gives me that f of v sub x is a subset of v sub y. Since b sub x is a subset of v, then the image of b sub x is a subset of the image of v. But the image of v is b sub y. So I've got f of my one ball is a subset of my other ball. That's what I was trying to show. F of my one ball is a subset of my other ball. Okay, so now we gotta go the other direction. 3, or not 3, where did that number come from? 6. Now assume that, basically now we need to assume this condition. That for all x in x and for all epsilon in the positive real numbers, comma, there exists delta in the positive real numbers such that the image of the ball centered, the ball using x's metric, centered at x with radius delta, is a subset of the ball using y's metric, centered at f of x with epsilon's radius. Okay, so kind of reset our picture here. Rid of the orange here. Get rid of that. Okay, so what are we assuming? We're assuming that anytime you choose a point x here, and anytime you give me an epsilon here, then I can always find a ball around x such that it maps into this ball. That's what we're assuming. My job is to show now f is continuous. So how do I show f is continuous? How do we show a function's continuous?
Showing that its preimage is open.
Showing that the preimage of an open set is open. So I need to pick some random open set over here and show that its preimage is open over here. So I'm going to pick some random open set over here. So here's how we're going to start this. Let me kind of walk you through the logic and then write it out again. So here's how we're going to start this. I'm going to come over here and I'm going to pick some random open set, V. And I'm going to look at its preimage. Over here, U. I know V is open. I'm trying to show U is open. I know that, so what I'm then going to do is, I can show that U is open if I can show that anytime you choose a point in U, call it X, I can find a little ball around X such that that little ball is a subset of U. That's what I'm about to do. How do I know that? This right here. What does it mean for a set to be open in metric topology? It means that for any point in it, you can find some open ball containing that point where it's a subset of all of it. So I start out with, here, 7. Let V be open in Y, comma, and let U equal the pre-image of V. So my whole goal here is I'm trying to show U's open. Comma, sorry, weirdly, English, and let X be any point in U. And let X be any point in U. So I pick a random open set over here, V, look at its pre-image U, and pick a random point X out of there. If I can show that I can create some open ball around X, then we're done. Because then I showed for any point X you choose in U, I need to show how to get an open ball containing that point X that's a subset of U. If we do that, U's open. Now how am I going to do that? I'm going to have to use this fact, what we assumed here. Or sorry, I have it listed out here. We're going to have to assume this. What did we assume? We assume that for any point you choose, okay, there's my X, and for any epsilon, for any radius we have over here. We don't have a radius over here yet. So let's get that. So little x is over here. F of x has to show up somewhere over here. I have no clue where. So f of x has to be somewhere in V. I have no clue where. Now since f of x is in V, and V is open in Y, for sure V is open in Y, right? Yeah. Then I'm guaranteed that there must exist some radius around f of x such that that ball is a subset of U, or of V in this case. So since f of x is in an open set, I'm guaranteed that there's some epsilon I can create around f of x, some epsilon, such that that open ball is inside of V. So 8. Since f of x is in V, comma, there must exist epsilon in the positive real numbers such that the open ball, I'm going to call this open ball, I'm not sure if I'm going to need a reference again, so I'm going to call it B sub y, such that B sub y equal to the open ball using Y's metric centered at f of x with radius epsilon is a subset of V. Since V is open in Y, I'm guaranteed, and since f of x is a point in there, I'm guaranteed that there's an open ball centered at that point completely contained within V. Now, by assumption, remind you of our assumption since it was kind of a big one. What was our assumption? Our assumption was anytime you have an x here and a radius and an open ball around f of x over here, I can find an open ball around here that mapped completely in there. So then by assumption, there exists delta in the positive real numbers such that, I'm going to call the ball B sub x, such that B sub x equal to that ball, such that the ball using x's metric centered at x with radius delta such that the image of it, sugar. So, we won't name it. Such that the image of that ball is a subset of B sub y, is a subset of this ball. So I'm guaranteed that there's some open ball around here with some radius delta, such that when we map it through, it's a subset of that. 10. Then, comma, since B sub y was a subset of V, then the ball, using x's metric centered at x with radius delta, is a subset of U. since the image of that ball is in V, and U is a preimage of all of V, then the preimage of that open ball, which contains that, must all be in U. So there we go. I found an open ball containing X in U that was completely a subset of U. So 11. Then U is open by theorem, what we call theorem 1. 12, therefore, F is continuous. And we're done. All right, that was a bit of a mouthful of a proof. Hopefully the picture helped. This is very abstract stuff. You're like taking the hardest part of calculus and then looking at it in an even more abstract way. So it's a lot to swallow. It's a lot to take in. Did you have any questions on that? Anything that feels weird? Good. All right. Just you guys, this is moving too fast. Barely a half hour in. Okay, hopefully you can see that. Okay. So our next theorem, let D and D prime be metrics on some set X that induce topologies tau and tau prime. Now the way the author says this is, then tau prime is finer than tau if and only if, let me say this with high-level language first, and then we'll read that carefully. First off, intuitively, what does it mean for one topology to be finer than another topology? What's finer, sand or rocks? Sand's finer. It's broken up into smaller pieces. The open sets are smaller. There's more of the open sets. And so, if tau is a subset of tau prime, which one has more elements in it, tau or tau prime? Tau prime is the one that has more in it. Everything that's in here is for sure in here. There could be things in here that aren't in there. It could be the same, or this one has more. So that's what we mean. That's mathematically how we communicate. One set is finer than another set. It has all the pieces that this one has, and then some. It's broken up into more pieces, possibly smaller pieces, finer pieces. Okay, we're going to say one topology is finer than another if, with the coarser topology, so looking at our coarser topology, here's one of its open balls. If with the finer topology, I can always create smaller open balls inside of its open balls. So imagine that tau prime had the Taxicab metric, and tau had the Euclidean metric, just for the sake of the picture. Since anytime you have an open ball using the Euclidean metric, I can always create a smaller open ball using the Taxicab metric, then it's a finer metric. Now I happen to pick two metrics equivalent because it's also the case that for any Taxicab metric you choose, I can find a smaller basis element inside of there. So they're both finer than each other, they're both subsets of each other, therefore they're equivalent. So maybe a bad example there. But hopefully the intuition is there. How do I know one's finer than the other? If one has basis elements so small, they can always fit inside the other one's basis elements. The one with the smaller basis elements is the finer one.
Like sand could fit in rocks, but rocks can't fit in sand.
Correct. That's one way to think about it. If you somehow hollowed out the rock, you fit a lot of sand inside a rock, can't fit a rock inside a grain of sand. So yeah, the finer ones, we can fit its basis elements into the coarser one. That's what we're going to prove. So now let's read it exactly as it's stated here, and hopefully it makes sense. So then, tau prime is finer than tau, if and only if, for any x in x you choose, and for any epsilon you choose, I can find some delta such that my basis element, using the finer topologies metric, is a subset of the basis element using the coarser topologies metric. So don't get confused. Notice how if the subset is that way on there, it's flipped on here. This one's saying the tau is a subset of the tau prime when the tau prime's metric is a subset of the tau's metric.
Right.
Good? Okay, so I think if you get past that confusion, we're good to dive in. So that's one thing that made me double take when I read that. Because I saw subset going one way and then the opposite way on the balls. Okay, so let's prove it this way first. So this is an if and only if proof, so we're going to assume this is the case, show that implies this is the case, and then vice versa. So start out with one, assume tau is a subset of tau prime. And now what are we trying to do? I'm trying to show that for any point you choose in X, maybe should have said one more thing. Notice that both these topologies are being defined on the same set. Before we were talking about mapping from one topological space to another. Now we just have one set. We're talking about two different topologies on the same set, or two different metrics on the same set. Kind of like the Taxicab metric and the theorem metric, both on R2. Okay. So what's our job? My job is to show that for any x you choose and for any epsilon you choose, I can always find some delta that satisfies this condition. So assume tau is that. Let x be any point in X, comma, and let epsilon be any positive real number. No clue what it is. But regardless of what it is, I need to show how to find a delta that satisfies this condition. Okay, 2. Since the ball using D's metric, I'm going to set up this ball here. Since the ball is centered at X with radius epsilon, what do I know about that ball?
It's going to be coarser than tau prime, or other way.
I need to come up with a way to set up a ball here that's finer than it, smaller than it. So that's what I'm setting up to do. What information do I have about this ball from what we assumed here? Maybe it's too big of a leap. This ball, I know, is an open set. A ball is always an open set. So this ball is in what set?
Is it a tau?
It's in tau. This ball is in tau. Remember, D is a metric that we use to create tau. D prime is a metric that we use to create tau prime.
Yep.
This is one of the open balls we use to generate tau. So it's in there. It's an open set in tau. Perfect. So I know it's in tau. Since I know it's in tau, what do I know?
It's also a tau prime because tau
Perfect.
is a subset of tau.
So that gives me that that ball is in tau prime. So now it's an open set in tau prime. Now, it's an open set in a metric topology. So I know that whatever this looks like, X with epsilon, whatever it looks like, I know it's an open set in a metric topology. What do we know about open sets in metric topologies? Back to what we call theorem 1.
That they're open if you can find some.
If for any point in it,
You can find a
Find
ball
radius
set
that
up.
points entirely.
yeah, so now using the D prime metric, for our picture we're going to pretend it was a Taxicab metric. There has to be some open ball I can create centered at X. So this was epsilon. There has to be some open ball I can create centered at X with radius delta, such that it is completely contained within this open set. So this open set, if we just think about as U for a second, as the open set, and we read what theorem 1 says. Theorem 1 says, use open if and only if for any point you choose in there. We can create an open ball around that point. That's completely a subset of U. Using its metric. So using D prime's metric, I can create an open ball here, centered at that point. That's completely a subset of U. So that gives me that. So 3. Then by theorem 1, we call it, comma, there must exist delta in the real numbers such that the open ball, using now D prime's metric, centered at x, because we were saying this is an open set in tau prime. So the open ball using d prime's metric, centered at x, using delta, is a subset of this ball. Okay, so we proved this one way. I just really showed that if tau is a subset of tau prime, then I can find an open ball using the prime metric that's a subset of any open ball you choose using the d metric. You picked any x and epsilon you want. I found an open ball that was a subset of the ball you chose. And I can do that for any ball you choose. We didn't assume anything special about x and epsilon. Okay, so now we gotta go the other way. So now assume this messy condition. Now assume for all x in x and for all epsilon in positive real numbers, there exists some delta in the positive real numbers such that the open ball using the prime metric centered at x with radius delta is a subset of the open ball using the d metric centered at x with radius epsilon. Okay. My job now is to show that tau is a subset, up here. My job now is to show tau is a subset of tau prime. How do I show one set is a subset of the other?
You show that all its elements are in that set.
I show anything you choose in here, here it is, anything you choose in here is also in here. So I'm going to grab something random out of there and show that's also in there. Okay, 5. So let U be any open set in tau. Okay, let U be any open set in tau. And I'm trying to show that U, when it's all said and done, I'm also trying to say that U is in tau prime. That's where I'm trying to get. Now, the way that I argue U is in tau prime is I'm going to say that U is also open using the d prime metric. How am I going to show that U is open using the d prime metric?
You can show that you create a ball around it.
Theorem 1. I'm going to show for any point you choose in U, I can create a ball around it that's a subset of U. So I need to also grab some random point in U. So let U in tau, comma, and let x be any random point in U. I need to show that I can create a ball around x that's a subset of U. A ball using the prime metric, not the d metric. I already know I could for free using the d metric because U was open using the d metric. Okay, so 6. Since x is in U, then it must have been in some open ball centered at x using d's metric. Since it's open using d, since U is open using d's metric, then and x is in U, then there must be some open ball centered at x that's a subset of U. So since x is in U, that gives me that there must exist epsilon in the positive real numbers such that the ball centered at x with radius epsilon is a subset of U. Now, by assumption, what did we say by assumption? 7. By assumption, we assume that anytime you found an open ball using d's metric, you can find a smaller ball using d prime's metric. So then by assumption, there exists delta in the positive real numbers such that the open ball, sorry, this was using d's metric, this is using d prime's metric, such that the open ball using d prime's metric centered at x with radius delta is a subset of the open ball using d's metric centered at x using radius epsilon. Let me squish this a little bit more. Using epsilon, which is a subset of U. So I just barely showed that for any x you choose in U, I can find an open ball using d prime containing that point, that's a subset of U. So U is also open in the prime topology. So then U must be in the prime topology. And there it is. Any questions on that? Can you think about it for a second?
I'm kind of struggling with what it means for one basis element to be smaller than another one.
So remember, since both these metrics are defined on the exact same set, then what we mean by one ball is smaller than another is it completely fits in there.
Centered at the same point.
Centered at the same point. We keep always centering at the same point over and over again.
Okay. Yeah, that makes more sense.
Okay. Quick corollary of this, I'm not going to write it out, but the standard metric and the Taxicab metric, and also the max metric, the three metrics we showed you last time on R2, they all give you the exact same topology. How do you know that?
Because
So-
you fit all of them within one another.
Right. Using the standard topology, pick any basis element from the standard topology you want. I can always pick an open ball, pick any open ball using this from the standard topology you want. I can always find an open ball using the Taxicab metric smaller than it. And so the Taxicab metric is finer than the standard one. But since I can also do the reverse for any open ball in the metric topology, I can also find an open ball centered at the same point. And the standard topology is smaller than it, then it's finer than the Taxicab one. Since they're both finer than each other, they're equal to each other. Oh, that was the Taxicab one. Taxicab metric. Its open balls look like the diamonds.
Yeah, because it's going in squares.
Oh,
Right.
that's right.
Now the author proves this. I didn't bother proving it because it's just a bunch of algebra. You just need to take your basis element. So if we were proving that the Taxicab is finer than the standard topology, we'd have to take a basis element, and then we choose the points here, 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 and here to get this one. And then it's just some algebra arguing that if you pick a point inside the Taxicab one, it's also inside of this one. So there's not much to be gained from it. It's just a big exercise in algebra. That's why I didn't bother doing it. But you can read this. Okay. Our next definition. Whoa, we completely skipped a definition. Because I proved 513. Oh my goodness. All right. Can't believe I skipped that. It's no wonder I was surprised by how fast we got through this board. Okay. Don't really need the whole board for this, but. All right. Definition. This definition is going to give us our definition for the distance between two sets. So the metric already tells us the distance between 2 points. That's built into the metric. We want to now be able to use a metric to tell us the distance between sets. So let's just establish some intuition really quick. Imagine that we're talking about in R1, so the real number line. I have the set A, all the numbers from -2 to 0, and the set B, all the numbers from 1 to 3. What would you say is the distance between those two sets?
1 probably.
1 is a pretty natural choice to use, right?
Yeah.
Because 1 is the distance from the end of this set to the start of this set.
Yeah.
So you might think, okay, we'll take the biggest element in this set and the smallest element in that set, we'll calculate their distance, and whatever that comes out to, we'll say is the distance between the two sets. Right? Or in other words, pick the points, the 2 points that are closest to each other from each set, and whatever their distance is, we'll call that the distance between the two sets.
Okay.
You see it?
Yeah.
Okay, let's throw a wrench into that. Now imagine that we have these two sets. So A goes from -2 to 0, B goes from 1 to 3. This time we don't include those points. So what is a point in A closest to B? It's not 0, because 0 is not in there. Is it -1/2? -1/4? -1/1000? -1/1,000,000,000,000?
You can't find it.
There isn't a closest point. There is not a point in A closest to B. It's kind of like asking what's the biggest number. Any number you choose, there's always a bigger number. What's the point closest to B? There isn't one. Any point you choose here, I can always find one a little bit closer. Similarly, there isn't a point in B closest to A. And yet, just intuitively speaking, what would you expect the distance between these two sets to be?
Slightly larger than 1.
Slightly larger than 1? Like what? Like 1.00001? Or should it be 0.0000001? What does slightly mean?
Approaching 1.
Set it up as some sort of limit?
Yeah.
Well, then in the limit, it's going to come out to 1.
Yeah.
And so you see, naturally you want to say that the distance between these two sets and the distance between these two sets are the same.
Yeah.
Both of them you want to say the distance is 1. Doesn't really make sense to pick any other number. Okay, so whatever our definition is, it needs to be able to accommodate that. So it's going to be slightly different than what you think. The naive way to say it is, we'll just pick the elements are closest from each set, whatever their distance is, we'll call that the distance. That's the naive way to say it. We run into problems with that.
Could you find the distance between the midpoints of each set, and then find a way to divide that?
That would be another way to do it, but now we need to find what the midpoint of a set is.
That seems easy.
And now you need to find the point. If you're going to talk about the midpoint 2 here, what's that the middle of? You're saying 1 and 3, which are not elements of the set. And so you're going to run into a similar problem there, where you need to be able to reference these boundary conditions.
I see. Okay.
Because imagine, here's how I think it will really help your intuition. So you would agree that the middle of this set is 2, right? Now imagine that we included 3 over here, but we still didn't include 1. Should that shift the middle over that way a teeny bit?
Yeah. Well.
But it can't. The middle has to stay 2.
Okay.
So you see how you'll run into the exact same type of problem if you try to carefully think it through.
Yeah.
So we got to deal with this problem. Let me give you 2 more pictures to give you some intuition, really help you see the problem before we give you the definition. So now we're in R2. Right? We're looking at this segment B, this segment A. What should the distance between those sets be?
Well, they're touching.
Yeah, they flat out intersect each other.
So 0.
0. There's no distance between them. They're touching. Right?
Okay.
So we're going to call those touching, so the distance between them is 0. Notice how this is different from when the distance between 2 points is 0. When the distance between 2 points is 0, that meant they're one and the same point.
Yeah. Right.
Those sets are not one and the same. Similarly, one more time, we've got this open set A here, and it's tangent to the x-axis but doesn't include it. And B is this portion of the x-axis. So now A and B have no points in common. What's the distance between them?
0.
Still has to be 0. So the distance between two sets can still be 0 even if they have no intersection, no common elements. Right. So now that we got some of the intuition for what we want this distancing to be, let's get its definition. Let X be a metric space, let A be any subset of X, and B be some other subset of X. Same thing we've been doing in our pictures. The distance between A and B is defined by the distance from A to B is equal to the greatest lower bound of the set of the distances between any 2 points in A and B. So we're taking a set of all possible distances. So little a, so create one of these sets. So I'm going to write out this set here for a second. So writing out that set, what do? We pick a random little a and a random little b. We calculate their distance. I calculate their distance, and in that case it came out to 2.6793 repeating, right? Now pick another A and B. Here's an A, here's a B. Calculate their distance. In that case it came out to 1.392 exactly. Do that for every possible A and B. Write out all their distances. Now, the distance between A and B, we're not going to say is the smallest thing in there, because that may not have the smallest thing. If we were doing it with these sets, we would never get a smallest thing.
Oh, yeah, I gotcha.
Instead, it's going to be the greatest lower bound of this set. Notice that this set will get arbitrarily close to 1. In this case, if we were looking at this picture, in this case, it would get to 1.
Yeah.
And that would be the smallest element in there. In this case, it would get arbitrarily close to 1, but wouldn't quite include 1. In either case, 1 is a lower bound of the whole set. Everything in this set would be greater than or equal to 1, with this picture and with this picture.
Yeah.
So it's the greatest lower bound you can find. It's a lower bound because everything in the set is greater than or equal to it. And if you picked a slightly bigger lower bound, it would a slightly bigger number than 1, it would no longer be a lower bound. So this number is a lower bound for all those distances, and it's the biggest lower bound you could possibly find. Notice 0 is also a lower bound. All the distances will be greater than 0. So 0 is a lower bound. But it's not the greatest lower bound we can find. The greatest lower bound we can possibly find is 1. Now it's a proof in calculus that every set of numbers has a greatest lower bound and a least upper bound. So unfortunately that relies on a result from calculus, but if I accidentally say infimum or supremum, stop me. It's just another way of saying upper bound and lower bound, but I don't want you to have to memorize terminology that you're only going to use for class. So that's the definition. The distance from A to B is the greatest lower bound on all the possible distances between them. Find the biggest number you can that is less than or equal to all the possible distances.
That makes sense.
Okay. Notice, well, question. Is this a metric on sets?
Yeah. Well, I mean,
Does this give us, is this new D that we defined to give us the distance between sets, does it give us a metric on the sets?
yeah.
Like if we added some other set C, for example, C is over here, will the distance from A to B plus the distance from B to C always be greater than or equal to the distance from A to C?
Yes.
Yeah.
Let's see, what's the distance from A to B?
0.
0. What's the distance from B to C? It's that.
Right.
What's the distance from A to C? It's that. The distance from A to C is way bigger than the distance from A to B plus the distance from B to C. So it doesn't satisfy the triangle inequality.
So weird. Okay. So it's not a metric,
So it's not a metric.
but you can still find distances.
It happens to be symmetric. Sorry, it happens to be symmetric, but it doesn't satisfy this, the triangle inequality. And it also doesn't satisfy this. It's true that the distance will always be greater than or equal to 0, but this second part is not satisfied.
Yeah.
The distance can be 0 without the sets being identical. So it doesn't satisfy the first condition, and it doesn't satisfy the third condition. So even though we use D to talk about the distance between two sets, this is not a metric. Can't remember which of my markers were good. Oh. Top of the battery. Maybe I left the good one over there. Okay. Did we cover everything on that board? Yes.
We proved theorem.
Yeah. Stopped at the theorem and then forgot to go back. Okay. Back to here. Not sure what I was doing on here that reminded me of it. Alright, let's just see if we can a little bit more over.
I think you were about to start on.
The next definition, I think.
Yeah, you're about to start on the next definition, but I remember you stopped the other time.
Yeah.
Oh, right. Talk about set being bounded. Okay. So now, let X, D be a metric space. Then a subset of X is bounded under this metric D, provided that there exists some number mu. Sorry, that's a positive number. Can't really say that. Just a common one that we use. There exists some positive number mu such that the distance for any 2 points in A, their distance is less than mu. So what does this mean? So here we got X, and then A is going to be some set, not necessarily open or closed, inside of X. We say A is bounded under a metric D. If we can find some number, let's pretend that we're talking about the Euclidean metric using like meter sticks. Well, we'll say using yardsticks. Notice that no 2 points in A can be more than 2 feet away.
Okay.
So mu equal to 2, understanding that our metric is using feet, mu equal to 2 would be a bound on A. No 2 points, that's not a point, let's just mark on that. No 2 points in A can be more than 2 away. That's as far away as they can possibly get. Or if you say to, well, for sure 91 feet, none of them are 91 feet apart. We don't need to be clever and find that minimum number that captures them, just some number. If you can find some number such that the points will never be more than that distance away, then we say that the set is bounded under that metric D. Maybe under a different metric it's not bounded, but under that metric it is. Okay. If we can find a mu for the entire space big X, then we say that the entire space is bounded under mu. So let me read the definition one more time to make sure I didn't accidentally say something wrong. So let X be a metric space, then A as a subset of X is bounded under D, provided that there exists a mu in the positive real numbers, such that for any 2 points in A you choose, the distance between them is less than mu. If the entire set X is bounded under D, we call D a bounded metric.
It can't be less than or equal to mu?
If you say less than or equal to mu, then it would be for sure less than mu plus 1. So if you can find a mu that's less than or equal to, you can find a mu that's less than.
Oh. Okay.
So you can put the equals there if you want, it doesn't really change anything. All right. So let's think about this for a second. This notion of a bounded metric means all the points can't get more than some distance away from each other. Now if we're using the standard metric on R2, is R2 bounded?
No, because it can go on.
No. For any distance you choose, I can always find 2 points even further than that distance away from each other. And since we found one metric that makes so R2 isn't bounded, then for any other metric you choose, R2 must not be bounded, right? Because R2 is infinite, so we can always pick points further and further away. You see that? Good, because that's wrong. And we're going to prove that that's wrong. So, we're going to come up with a metric that we're going to put on R2. Under R2, it's going to be bounded using that metric. There's going to be a max distance 2 points can be away from each other. And you can't find 2 points even further than that away. And here's what's even crazier. That crazy metric we come up with, it's going to give the exact same topology as the standard metric does. But we're jumping, actually, we can do the proof and then come back to this. Don't let me forget to come back to this. All right, so come back to this definition after. We'll jump over to this proof. All right, so let XD be a metric space. Then D prime is going to be, so we're defining a new metric. So we have X and D here. D's for sure a metric. In our heads, we're going to think about X is R2 and D is the standard Euclidean metric. Okay. Then we're going to define D prime. It's going to take 2 elements out of X, whatever our set is. And it's going to spit out R. So we're defining a metric. And it's going to be defined by the distance between X and Y using D prime is going to be the minimum out of whatever your metric was already spitting out and 1, whatever smaller. So let's get a feel for this really quick.
Oh,
Pick 2 points here. So I pick x here and y here. X, y. Now using d, then the distance between x and y might be something like, I don't know, 13. Using d prime, what's the distance between x and y?
What's the,
It's just 1.
well,
It's the minimum out of whatever d spit out in 1. Whatever's smaller. What's smaller, 13 or 1?
1.
So it spits out 1. Using d prime's metric, now if I pick y close to x, so now their distance came out to 1/2. What's their distance when I use d prime? 1/2. So you notice that when the points are close to each other, this behaves the exact same way as that does. But when the points aren't close to each other, they behave wildly different. So jumping the gun a little bit, that is why the topology that this gives us is going to be identical to the topology that this gives us. Because locally, they both behave the same. When you're talking about really small. So anything that this says, yes, those 2 points are close, this one's going to agree, yes, those 2 points are close. It's not going to agree about distances over on big scales. But topologies don't care about distances on big scales. As long as things that were close are still close, we're good. And so since these locally behave the same, since they behave the same on really small scales, then they're going to agree about what is close and what is not close.
So could you just make 1 an arbitrary number?
So 1 is a completely arbitrary number. I could have made that 1 1,000th, 1 1 trillionth, 1 whatever you want. And it has no effect. We're just going to use 1 because it's an easy number to work with. But yes, that's a good point. Okay, so that's what we're proving here. So let xd be a metric space. Then d prime, defined this way, is going to be a bounded metric, and it induces the same topology as d. So 1, it's a bounded metric because now the furthest 2 points can be away from each other is 1.
Right. Wow.
So it's bounded by the number 57. No points are more than 57 units apart.
Feels like cheating.
It feels like cheating.
Yeah.
All right, well, let's be sure that's not cheating. So before we do this, we need to prove that d prime is in fact a metric. So let's check that first. So property number 1. We need to make sure that d prime only spits out numbers greater than or equal to 0.
Right.
Now notice, d we already know is a metric.
Yeah.
So this is always greater than or equal to 0.
Yeah.
And 1 is always greater than or equal to 0. So d prime for sure only spits out numbers greater than or equal to 0. Okay, we're good there. Next, when is it 0? When does d prime spit out 0?
When x and y are the same.
When d spits out 0. The only way this can be 0 is if this is 0.
Okay. Yep. Yep.
And this is only 0 when x and y are the same point because we know d is a metric already.
Yep.
Okay, so that satisfies the first property. Second property, which is the distance from x to y is equal to the distance from y to x. The distance from x to y is always going to be equal to either 1 or what this spits out.
And that's metric.
This spits out the same thing if it's x to y or y to x.
Right.
So this is always going to spit out the same thing if it's x to y or y to x. Because it's always going to spit out what this was spitting out, whereas it's going to spit out 1. In either case, it's spitting out the same thing in both cases. So the triangle inequality is the only one that's kind of weird here. When we start looking over long distances. Longer distances, right? Adding things up. So I know that d satisfies the triangle inequality. So I know that the distance from x to z is always less than or equal to the distance from x to y plus the distance from y to z. I need to prove that that's also the case with d prime. Okay? Now I'm going to handle 2 cases. So if d from x to y is greater than if it's equal to 1, then we can still spit this out. So I think this is fine. I'll say greater than or equal to. If it's greater than or equal to 1, or the distance from y to z is greater than or equal to 1, then we have that d prime's distance from x to z, d prime's distance from x to z, we already know that this is always less than or equal to 1, because d prime can't spit out a number greater than 1. But now, if I know that this number is greater than or equal to 1, and this number is greater than or equal to 1,
And the other has to give you a number greater than 1.
So it's just 1.
let me write it this way. So then d prime from x to y maybe I can just write it and you'll see it. Which this has to be less than or equal to d prime from x to y plus d prime from y to z. If d from x to y is greater than or equal to 1, then this has to be 1. Or if this is greater than or equal to 1, this has to be 1. 1 plus something, or 1 plus something, has to be a number greater than or equal to 1. Okay, so I get d prime from x to z is for sure less than or equal d prime from x to y plus d prime from y to z. You good with that case? Okay, so let's handle the other case. If d from x to y is less than 1 and d from y to z is less than 1, so if either of them were greater than or equal to 1, we already handled that. So now we got to handle the case where they're both less than 1. Then notice that this one is equal to d prime from x to y, and this one is equal to d prime from y to z. Because when the distance is less than 1, they spell out the same thing.
So it's not d prime, it's just d, isn't it?
The distance from x to y using d is the exact same as the distance from x to y using d prime, if its distance is less than 1. Similar over here.
But when you say d prime, that could also be referring to 1, couldn't it?
So if I know that the distance from x to y is less than 1, then d prime, what does d prime spit out? D prime spits out the minimum of d and x and y and 1.
Right.
In that case, since this was less than 1, d prime just spits out this.
So,
It can't spit out 1 since this was less than 1.
or why are you calling it d prime? You could just call it, well,
It's saying it's equal to.
right. Okay.
Maybe I ran it that way. Just for so then, the distance from x to y is going to, the d prime's distance from x to y is just equal to, it gives me the minimum out of those two things. Since 1 is bigger than this, in this case it's just going to be equal to dxy, and d prime from y to z is just going to spit out the distance from y to z using d.
Right. Okay.
Okay. So then the distance using prime from x to z. Notice that the distance, I'm writing with too much space. I want to write this in one line. So then the distance from x to z using prime. Notice that whatever number the prime one spits out is always less than or equal to what the d spits out. D can spit out numbers bigger than 1. This can only spit out numbers less than or equal to 1. If this spits out 10, this spits out 1. If this spits out 1/2, this spits out 1/2. So this either spits out the same thing as this or something smaller than this. So d prime from x to z is always less than or equal to d from x to z, right? And now d from x to z, we know that d satisfies the triangle inequality. So this has to be less than or equal to d from x to y plus d from y to z. But up here we show d from x to y is d prime from x to y, and d from y to z is d prime from y to z. So this is less than or equal to, I'll just write down one, d prime from x to y plus d prime from y to z. And so I get d prime from x to z is less than or equal to d prime from x to y plus d prime from y to z. Okay, so it is in fact a metric. Yay, we got that. now let's get on with our proof. Unless you have any questions about how it's metric. I feel like I skipped something.
That makes sense.
Good?
Yeah.
Okay. Alright. So, we proved that's a metric. And then obviously it's a bounded metric. So, didn't need to really specify that more. So now we just need to prove that it induces the same topology as D. So let's name those. So let tau and tau prime be the topologies induced by D and D prime respectively. Respectively just means maintaining order. Okay, 2. I'm running with way too much space there. I'm trying to show that these topologies are the same as each other. So I need to show that tau is a subset of tau prime and tau prime is a subset of tau. Now I have a condition for showing tau is a subset of tau prime. I need to pick one of tau's open balls and show that I can find a tau prime open ball that fits in it. Okay, so let's do that. Let the ball using, let's see, which one should I show first? Let's show that tau is a subset of tau prime. The way that I'm going to do that is show that there's a tau prime ball that's a subset of tau. So first I need to get a tau ball, and then come up with that ball. So let the balls using D, centered at X with radius epsilon, be an open ball, obviously it's for D, comma, and let delta equal the min of epsilon and 1. So, starting with some random open ball, using our Euclidean metric, has some random epsilon, I'm going to have to handle 2 cases. Because in one case, epsilon is bigger than 1. In one case, epsilon is greater than or equal to 1. In another case, epsilon, another possible picture could be like this, where epsilon is less than 1. Right? So here's my 2 possible pictures. What I'm going to do is I'm going to pick delta to be the minimum of epsilon and 1. If epsilon was greater than or equal to 1,
Pick 1.
if epsilon is greater than or equal to 1, I pick 1, and so my ball is just going to have a radius of 1, and it's going to be that ball. On the other hand, if epsilon is less than 1, then my delta is the same thing as epsilon, and so my ball is going to be the exact same ball. Okay, so let's see the best way to say that. So 3. And if epsilon is greater than or equal to 1, comma, then the ball using D prime's metric, centered at X with radius delta, is going to equal the ball centered at D prime x1, right? If epsilon is greater than or equal to 1, my delta is just going to be 1, which is going to be the same thing as the ball using D's metric centered at X with radius 1. Because at 1, they both get the same thing. Which is going to be a subset of the ball using D's metric centered at X using radius epsilon. And so I showed this ball is a subset of this ball. Now we need to handle the other case. 4. If epsilon was less than 1, comma, then the ball centered at x using delta is the same thing as the ball centered at x. Sorry, this is using metric d prime. Is the same thing as a ball centered at x using metric d using radius epsilon, which is a subset of itself, if you want to say that. That's probably good to write to remind ourselves what we were after. Okay, so 5. Then, what did we just barely show? So we showed in either case, we were able to find a prime ball that's a subset of the non-prime ball. And so we just barely showed then tau is a subset of tau prime. That's what we've shown so far. Now we gotta go the other way. So 6. Now we let the ball using d prime centered at x and epsilon be open in tau prime. So now in this other case, let's think what is our delta going to be. Our delta in this case is just going to be epsilon, but let's walk through it for a second here. So this time now, I start with a ball open in d prime.
In tau prime?
Or in tau prime. An open ball using d prime symmetric.
Right.
Well, maybe I'll make sense of this. Maybe you'll see how this makes sense when we walk through the two cases. Let's walk through the two cases because one of the cases is really weird. 7. If epsilon is greater than or equal to 1, then what is the open ball centered at x with radius epsilon equal to?
1.
Using the prime metric.
1.
What are all the points whose distance is less than, oh wait, epsilon needs to be greater than 1, can't be equal to 1. So we'll handle the case where epsilon is greater than 1. So if epsilon is greater than 1, what are all the points whose distance from x is less than or equal to 1? So epsilon is some number greater than 1. Let's pretend epsilon is 2 for a second. Because I need to say some number is slightly bigger than 1. We'll use 2 as an example. We're in the prime metric. What are all the points that are within a distance of 2 of x?
All the points that are within a distance of 2 of x.
Yeah, we're using the prime metric. What is the furthest away 2 points can be?
1.
1.
Right. Okay, I see. Okay, I see what you mean.
So if we're thinking about in R2, take the origin, and then take a point a trillion units to the right and a trillion units up. What is the distance between those 2 points using our prime metric? It's 1. So what are all the points within 2 of x?
1.
Every point is within 2 of x.
Yeah. Theoretically.
Because the furthest away 2 points can be is 1.
So if anything's farther, then it's in the 2 range because it's in 1 and 1.
Right? The furthest away 2 points can be is 1. So what are all the points? So I'm a point. What are all the points within a distance of 2 of me? Everything. Because the furthest away from me they can be is 1. So if epsilon is a number greater than 1, then all the points whose distance from x is less than epsilon is all of x.
Weird. Makes sense.
Makes sense. There's weirdness.
Okay.
So that gives me then that the ball using d centered at x with radius epsilon, whatever it is, it's for sure a subset of this ball. Because that ball is the whole space. And this has to be a subset of the whole space.
Right.
Okay, now we have the other case. 8. If epsilon is less than or equal to 1, comma, then the ball using d prime centered at x with radius epsilon is exactly equal to the ball centered at d using radius delta. Probably should have said that backwards. So then the ball centered at D using, this over here was supposed to be delta. But delta and epsilon are the same thing, so those are really rare. But, so then the ball centered at x using delta, that's just equal to the ball using D prime centered at x using epsilon. And so obviously that's a subset of the ball using D prime centered at x using epsilon. So then what did we just really show?
They're both a subset of each other, so that
Then tau prime is a subset of tau,
so they're same.
which gives me that tau is equal to tau prime, since they're both subsets of each other. Good?
Yep.
Okay. One more definition, one more example, and then we'll be done. So next definition. Let x with its metric d sub x and y with its metric d sub y be metric spaces, and let f be a function from x to y, where that function is a bijection. So got a bijection from x to y, 1 to 1 and on 2. Then we say that f is an isometry, provided that for any 2 points in x you choose, the distance between them using x's metric is equal to the distance between them when we run them through the function using y's metric. If an isometry exists between 2 metric spaces, we say that the 2 metric spaces are isometric. This is like homeomorphisms to topology. A homeomorphism, what was a homeomorphism? A homeomorphism was a bijection that was continuous one way and the other way. Or in other words, it was a bijection that also preserved proximity. It preserved the topological structure, it preserved proximity. An isometry is a function that's a bijection that preserves distances. The distance before you run it through the function, the distance after you run it through the function is the same thing. Let's just get a picture associated with this. I think you got it, but let's just get a picture just to be for sure. So here's x over here, it's a metric space. Here's y over here, it's a metric space. We have x here, we have y here, and we have the distance between them is 2. We run them through f, so we have f of x here, and we have f of y here. If these 2 things are isometric, or in other words, if this is an isometry, then the distance between them afterwards is still 2. So the distance between x and y, using the metric in x, is equal to the distance between f of x and f of y, using the metric in y.
So they don't have to be the same metric.
No, completely different metric spaces, completely different metrics. We could be mapping letters to numbers here. Completely different spaces.
Okay.
So, remember, since metric space is a stronger notion than a topological space, 2 spaces being isometric is a stronger notion than them being homeomorphic.
Right.
If they're isometric, they're for sure homeomorphic. But they could be homeomorphic without being isometric. Because we could be talking about 2 topologies that aren't even Hausdorff. And so they're not even, there's no metric to even talk about on them. Okay. So stronger notion. So, while we showed that the Euclidean metric and the Taxicab metric gave the same topology on R2, we're going to show that they're still very different metrics. And that those 2 metric spaces, if I take R2 and I give it the Euclidean metric, and I take R2 and I give it the Taxicab metric, those 2 metrics are not the same. They're not isometric. They do not talk about distances the same way. And we're going to kind of give a proof of that just through an example. So we're going to look over here. dt is going to be the Taxicab metric. D is just going to be the Euclidean metric. Okay. You with me? And erase that for a second. Okay. Let's pretend for a second that some function f exists such that f is an isometry. So let's pretend that it's going to map R2 to R2 in a way that preserves these distances, where the distances over here are going to be calculated with the Taxicab metric, and over here we're going to use the Euclidean metric. And we're going to pick 4 random points, A, B, C, and D. Now I label these 1, 1 so that we can calculate the distance using the Taxicab metric. So the distance from A to B, if you go along here, is just 1. The distance from B to C is 1. The distance from C to D is 1. The distance from A to D is 1. Just using the Taxicab metric. And what's the distance from A to C? 2. So going from A to C is the same as going from here to here to here. Similarly, what's the distance from D to B? 2. So we pretend this function exists, so it maps these points. We have no clue where it maps these points. It does not necessarily map the origin to the origin. It can map them anywhere. So it maps A somewhere, I have no clue where. And it maps C somewhere, I have no clue where. But one thing I do know is the distance between A and C now, using the Euclidean metric, has to be 2. Whatever it is, that distance has to be 2. Right? And now the point B here has to be 1 unit away from C and 1 unit away from A, using the Euclidean metric. And so C, the only way I can do that is if it's right smack in the middle of that segment. C, oh sorry, not C, B, thank you. I'm talking about B.
Oh, yeah.
Since B is exactly 1 unit from C and B is exactly 1 unit from A, the only way I can do that is if it's in the exact middle of the segment. Similarly, D is exactly 1 unit away from A and 1 unit away from C. So D also has to be exactly there.
However, D is 2 away from B.
However, D has to be 2 units away from B.
Then you can't draw that.
And it's exactly the same point. So their distance is 0, but their distance is 2. Contradiction.
So it's not an isometric.
So it's not an isometry. So those two metrics are not,
Isometric.
yeah, a metric space using the Taxicab metric and a metric space using the Euclidean metric, those are not isometric. And intuitively, we already understand that. They talk about distances very differently.
Right. Do you want to show it to the real fast? Just so I can help my intuition a little bit.
I don't know how to pick, no, I can't.
Oh, okay.
Because I won't be able to find another one on R2. That's not just a dumb way of restating this. So I'd have to come up with a metric on some completely different space. But any one that's different on R2 is going to be different on R2. And so it's not going to come out the way you want it. So no, I don't have a good example off the top of my head. But notice how these two metrics, which you might think they're just slightly different, when it comes to the isometry,
They're quite different.
they're not related at all. Yet, we went over here, we were talking about D, and then this D prime metric, which those are drastically different. And yet they spat out the same topology.
Are they?
So these two spit out the same topology, these two spit out the same topology, so they would be homeomorphic. If we set up a space with one and a space with the other, they'd be homeomorphic. But not even close to isometric. Even these two weren't isometric and they're pretty close to each other. So homeomorphisms are a much weaker notion. Two things being homeomorphic is a much weaker notion than two things being isometric.
Right.
Isometric, much stronger notion.
Oh, okay.
Okay? Alright, so that's it for metric spaces. Now we'll go back to talk about properties of topological spaces. Next week we'll be talking about connectedness. How connected a topology is. You get from one point to the next point intuitively without leaving the set. Maybe, I don't know if we cover some graph theory in it. We might. Alright, see you guys next time.
Thank you.